In this experiment, we will be studying the chaotic behavior of a nonlinear pendulum by using a phase space plot. A nonlinear system is one where the output is not directly proportional to the input. In such a system, a change in a variable is not proportional to the change in variable at a later time. Our apparatus consists of an aluminum disc connected to two springs. One of the springs is connected to a driver. The frequency of the driver can be adjusted by adjusting the voltage given to it. A movable magnet is used to damp the oscillating disc. Also, we have a point mass attached to the disc to make the system nonlinear. The point mass attached to one end of the disc makes it biased and hence nonlinear. So, what is chaos? Chaos deals with the study of behavior and condition of dynamical systems that are highly sensitive to initial conditions. In such systems, a small difference in initial conditions can yield widely diverging outcomes, hence making long-term prediction of the state of the system impossible. Now let's talk of the damped forced oscillator. Here, the amplitude of oscillation depends on the frequency of the driver. If that frequency is equal to the frequency of the driver, resonance occurs. The system takes some time to respond to the change induced by the driver. This is called as the relaxation time. If the time period of the driver is almost equal to the relaxation time, the system may not be able to respond fast enough to changes induced by the driver. The system is forced to change state before completing the oscillation. This forms a repetitive pattern called doubling. When the frequency is further increased, a sequence of doublings is observed. The increasing frequency leads to an infinite sequence of doublings. The system becomes random and completely unpredictable. This phenomenon is called chaos. Here is an example of a phase plot. In this experiment, we'll be plotting the phase plot between angular velocity and angular position. The experimental setup consists of a voltage source, a nonlinear oscillator, and a Pasco 750 for measurements. We plot the potential well by first rotating the disc, and after clicking start, we let it go. We attach a mass by screwing it onto the aluminum disc. After that, we let it go so that it settles into its equilibrium state. Now, we plot the potential well once again with the mass on. To introduce damping into our system, we now attach a magnet and screw it to a distance of about 3 to 4 mm to the disc. Now we are going to plot the graph between angular position and time. We now introduce a voltage source to power up the motor for driving our oscillating system. There are two types of voltage adjustments, coarse and fine. The coarse adjustment changes the voltage rapidly, while the fine adjustment changes the voltage by smaller amounts. After introducing the driving force, we try to find the voltage at which the system oscillates in resonance. For this, we start increasing the voltage and study the graph for a sudden rise in the amplitude.
The graph you are seeing in this picture is similar to the graph obtained in the experiment from finding the natural frequency. Here, using crosswires, the time period between two peaks can be found out, from which the natural frequency can be found out by taking the reciprocal of the time period obtained. The graph you are seeing here is that of a damped oscillator. Observe the amplitude dying down. The damped frequency can be found out from this graph using the method as we have used before for the natural frequency. After we have found out the natural frequency omega naught and the damped frequency omega, a constant called as damping constant gamma can be found out using the equation omega naught is equal to under root omega square plus gamma square by 4. This constant gamma gives us the information about how the system is damped. If the value of gamma by omega is very less, then the system is lightly damped, and if the value of gamma by omega is very large, then the system is heavily damped. The graph that you see in this picture is that of a resonant frequency. As you keep on increasing the voltage of the driving force, you see resonance at some point. From this graph, you can see that the graph has peaked at one single point. The voltage at this point can be noted to find out the voltage at which the resonant frequency is obtained. After resonance is obtained, you can see that a similar pattern has been maintained, which is nothing but the doubling.